So in the previous part of this video, we talked about a half adder. We talked about how a half adder at the end of the day is the ability to take two bits, we'll call them A and B, and turn those bits into a sum and a carry out. And we can implement that, of course, using traditional logic gates as shown here. But we can also implement that as a series of equations, which you've just finished in this exercise operators example 2. We're going to continue to both look at the purpose, the overall design of things, and then how to implement that using Verilog, since that implementation allows us to scale what we're doing to the size of large designs. So let's go back to where we were. I'm going to navigate back to the top of the book by clicking on the index here. And we'll just go right back to our building blocks section and talk again about addition and subtraction. And we started by looking at a basic operation of adding two numbers. And we looked at the half adder so far. And we discussed how the half adder is a 2-bit add. Let's zoom into that one more time. So again, the big insight was that a half add is just what happens when we take two bits and add them together and produce a carry. You'll see the carry right up here and a sum down there. Now let's move to the next bit. That was a half adder, but notice that when we move to this next bit, we need to do something a little bit more complex. What we're doing here is we're actually adding 3 bits. Notice that we start with the carry in and add to that both A and B to produce a new sum and a new carry. Let's look at that sum and carry right now. Obviously, 1 plus 1 plus 0 gives us 10 in binary, so the sum would be 0, and our new carry is a 1. So like I said, what we need now is something that adds 3 bits and not 2 bits, and that is not the half adder, but we need a full adder. Here's the logic table with the usual thing. 1 plus 1 is 2, right? A 1, 0 represents the number 2 in binary. 1 is that carry out that's produced. And something that's new and unique in this logic table is when we have a 1 plus a 1 plus a 1, right? We get an A is 1, B is 1, we have a carry in of 1, meaning now we have a carry out of 1 and a sum of 1, right? We never got to the point in a half adder of having both a carry out and a sum. And if you look at the construction of a full adder, you can see quite clearly that what we've got are two combined half adders, right? There's a half adder right here, and then a second half adder right here. And then we're using an OR gate to combine the two carry results into a single carry out. And we're simply serially adding the first B with carry in plus A to produce a sum. So like I said, a full adder is simply two half adders chained together. Now let's spend just a minute and think about implementing that using Verilog. If you'll follow me, let's go take a look as we zoom in on that. We're going to go back to our main page as before and follow this combinational logic chapter and continue to work through our standard operators. But now let's go all the way to exercise 3, where again we have this schematic we've seen before. It's the full adder, which is composed of those two half adders, and now it's time to implement that. To make things a little bit simpler, we're breaking the implementation of the full adder into those two parts we talked about earlier. Here's our first half add right there, and what we're going to do is produce two values. We're going to produce the carry out from the half adder, and of course we're going to produce the sum of just that half adder. And you can see how we've implemented that in Verilog with two assign statements. The carry out is just B ANDed with the carry in. You can see that very clearly from the schematic here. The half adder sum is B XORed with the carry in, and now we've got those two values. It's your turn to write two assignment statements. We want to compute the final carry out value right here using that assignment statement. So again, you'll simply say assign carry out equals something, and that's of course going to involve our half adder carry out. as shown here, combine in some way with either A or B. I'm not even mentioning the carry-in input because, as you can see from the schematic, this carry-in input no longer directly affects the result. All the effects are filtered through the sum we've already computed and the carry-out we've computed from that half adder. Likewise, you're going to come up with an expression to allow you to assign a final value to the sum, again based on those same two values. Go ahead and complete this exercise. As before, the sum is just going to be the correct combination of course, now with the sum rather than the carry out, you'll be looking at the half adder sum. And A and B, complete the exercise. Don't forget to click save and run, work through the errors, make sure you got that correct. After that's done, unpause the video and let's take a look at the next topic.